Right, yeah, part 8 of 9 of our Key Stage 4 look at waves. So yeah, we're getting close to the end now. The last lesson we were looking at dispersion and total internal reflection. So this was sort of the last of 3 sort of sub-lessons really of how waves react to different mediums and how they sort of travel through those and what actually happens with the different types. We started off with reflection and refraction, so last week we were looking at dispersion and total internal reflection, and we're going to finish off now by looking at diffraction. So diffraction, what we're going to look at is we're going to look at the diffraction of 3 different types. We're going to look at diffraction of water waves, diffraction of light waves, and diffraction of sound waves, because although they share a lot of similarities, there are some subtle differences that do occur between them. So we're going to start off with water waves. So what do we mean when we say the word diffraction? So what's actually happening here is that we've got our water waves which are travelling up to a barrier. Now, generally speaking, the smaller the barrier, the greater the diffraction, but it's only up to a certain point. So what we can see here is that our wave has travelled through this small gap here and it's actually started to bend outwards. Now this bending of the wave is what we call diffraction. So what we actually have is the closer the gap that the wave is trying to get through to the actual length of the wave, then the greater the diffraction will be. Now I'm pretty sure that sounds fairly confusing, but what I'll do is try and explain it to you. So what we're actually going to say is that this dotted line is exactly the width, or exactly the length of our water wavelength. So as it travels through this gap, which is just ever so slightly smaller than our wavelength, as it goes through, our wavelength goes from being this big to being this big. And this movement, or this change in size, is what we call diffraction. So as you can see, our wave goes from being really quite small to working out into sort of a cone shape. And that cone shape is typically what we call the diffraction of a wave. So what's happening over this side? Well, our gap is actually much bigger. So what we'd actually have to do is put the equivalent really of having maybe 3 or 4 wavelengths wide. So what's actually mean is that the diffraction that's occurring is actually much less. It's only happening just out of the side. Instead of the whole wave being on there, it's really, it's not actually diffracting the wave very much at all. So it is all dependent on the actual size of the gap that the water wave is trying to work its way through. So as I said, the closer that the gap is actually to the wavelength, the more it will refract. If the gap, the more it will diffract. The greater the size, i.e. if it's much larger than the wavelength, then it really won't actually diffract it that much at all. So that's light waves. It just means it's basically it's the spread. Sorry, that's water waves even. That's the spreading of the waves as it goes through a barrier. So as I attempt to try and rub away all of the mess I've written all over there. So yeah, that's the diffraction of water waves. So the diffraction of light waves. Now, light waves diffract and behave exactly the same way as water waves do. But as we know, light waves are infinitely smaller than water waves. So in order to actually diffract them, you'd actually need a gap or a hole really, really small. I mean, on average, roughly, you'll be talking about a hole that's about 1,000th the size of a millimetre. So 1,000th of a millimetre. So that's a pretty tiny hole. You wouldn't, it's a ridiculously small hole. So to be able to actually split or diffract the wave, the light wave, as we can see here, has been diffracted out. We have a diffraction here. Then you would actually need a hole or a small gap, literally about 1,000th the size of a millimetre. But apart from that, it adheres to exactly the same concepts as diffracting a water wave. It's just because it's on such a smaller scale, it's that much harder to do. So finally, we're going to look at the diffraction of a sound wave. Now, sound waves are much larger, have a much larger wavelength than light waves do. So what actually happens again, depending on the source, the size of the source of the gap it's going through, will depend on the amount of diffraction that's happening. So the wavelength is longer, so therefore when it goes through a smaller hole, this wavelength is actually spread out much further, whereas if gone through a larger hole, the diffraction is actually not that greater in comparison to the actual size of the hole that it's coming out of. So when it's being compressed, as it reaches outside, it then goes back out. Now this alongside the refraction that we were talking about earlier in terms of sound waves being able to hit denser objects and vibrating through, this is also another reason why, because the wavelength is longer, it can bounce off and diffract off through doorways, down hallways, which is why, again, you can often see or you can often hear people from another room when you are stood down a hallway. It's because of the interaction between this diffraction and also the refraction as it goes through surfaces. But yeah, again, because the wavelength is much larger, as it goes through much larger than light, it's easier to diffract and diffracts quite regularly. So as it goes through a smaller object, it will disperse its way back out again, so it will travel for a lot further distance. So those are the subtle differences between the diffraction of water, the diffraction of light, and the diffraction of sound. So as I said, we've covered exactly what diffraction is and the differences between the three types. Now that's the penultimate lesson for our complete look at Key Stage 4. Our last lesson, which is going to be the next one, is actually going to be looking at the uses of waves. We briefly had a look in terms of how total internal reflections are used, and we mentioned some of them about the properties of reflection. But yeah, we're going to have an overall look of exactly what waves are used for in the modern day, and also some of the things that's not so good about them. Okay, so yeah, that's the end of today's lesson. My name is Ian McDowell. I'm a student at Bond University. Cheers.